SwayamPrabha. Digital India. Educated India.
Sir. Sir.
Yes, yes.
Sir, you are live now, sir. You can start your session.
Oh, thank you. A very good evening to all participants and stakeholders of Fundamentals of Theoretical and Experimental Aerodynamics NPTEL course, which we are rerunning during Jan to April 2024. And we are very glad to have many participants in this course. Let me introduce my team here before we move on. I am Professor Arnav Roy from Department of Aerospace Engineering, IIT Kharagpur, along with my team of TA students, Mr. Arpit Mishra and Mr. Arjun Garva, research scholars of Cryogenic Engineering Center, IIT Kharagpur. And the NOC 24AE04 is the code number of this course, which is being rerun this time. Because of active participation of many of the participants, we have found questions coming up on the forum, and we are going to address some of these questions, at least most of them, in fact, during this live session 1. We begin with a question from Tushar saying, can anyone please help me with the question discussed at the end of lecture 2? And he had some difficulties in working out the question. So our TAs have responded regarding the actual difficulty faced, whether it is the numerical part of calculating temperature, pressure, and density at 15 kilometers altitude, or was it the formulation part? So since it was not very clear what exactly was the point of difficulty, I would start by recapping a little bit of the fundamentals related to the solution. So we begin by recalling this plot where we look at temperature along the x-axis and altitude in kilometers along the y-axis. And from the sea level, the altitude spans up to 120 kilometers. And the temperatures that range over are from as low as 160 plus to around 320. That's the range we are showing over here, though the actual variations may be a little lesser than that, at least as far as the standard atmosphere calculations are concerned. As you may recall, we have the first gradient region here spanning up to 11 kilometers altitude from sea level. Then from 11 to 25 kilometers, we have the first constant temperature or isothermal region, followed by the second gradient region here up to 47 kilometers. 47 to 53 is the second isothermal region, and so on, till we range up to about 100 kilometers or so. Now, as we move along increasing altitude direction, let's say if that is the Z direction, then we may imagine a small control volume having a height dHg with a cross-section dx, dy along the xy directions, and two different pressures, P and P plus dP, acting on the bottom and top portions of that control volume, and then try to account for all the forces that may be acting on that air within the control volume. And we realize that from the bottom, it is this pressure which is acting, and from the top we have this pressure, as well as the weight of the fluid, which is calculated using the boxed expression, where this happens to be the volume of the fluid, times the density of the fluid at that altitude times the acceleration due to gravity. And as you may recall that when we looked at the geopotential approach, then it was one way of defining the G, while when we talked about the geometric altitude, we talked about a different value of G. In one case, we referred to the G at sea level as the reference, while in the other, we referred to it as changing with altitude, and therefore this G would actually become a function of H. And therefore, a slight difference in how we interpret the things. One thing that we have to be very careful about is the units as we use them. So I would recommend that you use the SI units consistently, temperature in Kelvin, then the pressure in pascals or Newton per meter square, density in kg per meter cubed, heights in terms of meters. If you are switching between meters and kilometers, you have to be careful about the calculations. And then, of course, G, whether you use it in the sense of G naught or you use it in the form of G as a function of H. In both the cases, you should be using the unit of meters per second square. Here was a question from Ronak, where he wanted to ask how is the air weight accounted in the calculations, and that is what we would like to re-emphasize, that it's basically coming from the equilibrium of forces along the Z direction as they work out for the control volume that we just showed over here. And from that, we derive a very important relation that the pressure change along the height of that control volume, which we demarcate as dP, essentially is denoted by this expression, which clearly explains that the dP, the pressure change as we move to a slightly higher altitude, would always turn out to be a negative change. That means it's basically a reduction that we are talking about. So this is something that we have to keep in mind. And another important issue that we have to look at is that when we look at the equilibrium of forces over here, it's primarily the forces along the Z direction which we are interested in, assuming that essentially these fluid elements are already in equilibrium in the off-plane directions. And then from the change in pressure that we calculated, we defined the connection between the change in geopotential altitude and geometric altitude. And thereby we brought in this relation where dH and dHg get connected through the two values of acceleration due to gravity, namely G naught and G. And we have a small note here as well to indicate that issue. And I guess by now, many of you may have actually solved some of these things, but I guess it may still be able to do a recap of the fundamentals. So when you integrate the above equation from sea level to a certain altitude, you get the relation between Hg and H. And I guess Tushar had a problem with difference in the R values that he has used, which comes up later. That's the next equation that we are looking at. That's the equation of state. But before I come to that, we need to integrate this relation and find the connection between H and Hg. And we can see for ourselves that for moderate altitudes, H and Hg are very close to each other. So we can approximately take H, because dealing with H has its own advantage, because we can go ahead with a G naught constant value in that case. Coming to the equation of state, we assume the medium to be a perfect gas, and P equal to rho RT is what we use, and we assume the specific gas constant as 287 joule per kg Kelvin. So you have to be careful about the units. And then we move on and set this equation, which will be the important equation to solve, whether it is for the isothermal condition or it is for the gradient regions. So when it comes to isothermal layers, inevitably the temperature goes out of the integral, because the temperature essentially remains constant. And when you are integrating the equation, you essentially take it from a height h1 to another, which is h, and then you get out a result of this form. When you plug it in to find the density ratio, you find that it again nicely simplifies, because the temperatures are identical, and therefore pressure ratio exactly matches with the density ratio. Going ahead, in the gradient layer, we talk about a lapse rate. That's the rate at which the temperature changes with altitude. And then you find that that can be denoted with a nomenclature A. And you can plug in that A into the expression so that you can express the integral in terms of temperature. There was a little bit of a slip in indicating the limits of integration. So please take note of this mistake, which I have tried rectifying here. And thereby you end up getting an expression for pressure ratio in terms of the temperature ratio. And if you move on, you find that there's a way to find the density ratio too, like we did before. In this case, of course, the temperatures won't cancel, so they remain here, and therefore there's an adjustment term in the exponent, as you can see. So that gives you the density ratio. The temperature changes with altitude as a function of the lapse rate, and therefore we have come to the end of the equations which essentially govern the calculations. And in this connection, Sagar Kundu has a question where he says that what should be the P1 value for the calculation from 11 to 15 kilometers. So this is a question related to the small problem we solved towards the end of lecture 2. So the response to that is that it would be the pressure that you calculate at 11 kilometers altitude using the gradient region calculations from sea level to that altitude. Therefore, it is the lower limit in the pressure integral. It is the pressure corresponding to the altitude from which you start integrating your equations. So you might have seen this nomenclature being used, that wherever we start the integration for a particular region, the lower limit happens to carry that subscript 1, while the upper limit doesn't have a subscript. So that's basically what it means. You have calculated from 0 to 11 kilometers. Whatever you get at 11 kilometers altitude basically takes up the 1 level. And then you move on in the isothermal region between 11 to 15 to perform your calculations, starting with those subscript 1 levels. So that's the idea. Now, let's try to move on from here. Just as a recapitulation, we have tried mentioning the numbers, the pertinent numbers once again over here. So as we move from 0 to 11 kilometers, we find that the temperatures are reducing at a rate of 6.5 Kelvin per kilometer. And we find that starting from a pressure and density of this kind at 11,000 meters, the pressure drops to a value of this, density drops to this, which are much lower. They are respectively 22 and 30% respectively of what they were at the sea level conditions. As you move from 11 to 15, you find that there is further reduction and the pressure reduces to this value, which is almost 12%, density to this value, which is almost 16% of what it was at sea level conditions. So this was what it was, and I hope by now most of you have been able to sort this out and get the values on your own. A few words of caution that you should keep in mind are that when you are performing such calculations, you should be careful with the units. You should be using consistent units, the nature of the region, whether it's a gradient or isothermal region, the starting values of the properties of that particular region, and the range of altitude for that particular region. So if you are keeping track of these aspects, then I don't see any problem that you might encounter. So good luck with the calculations. We move on to the next question by Prashant, where he says that he has a question regarding this particular video, where he's referring to the wing platform. And he has a question that whether it's the wing platform area that when we talk about, is it the projected area that we see in the top view, or it's the actual surface area of the wing? Now, the answer to that is that it's actually the projected area that you see in the top view. It's not the actual surface area, though for thin surfaces, there may not be very dramatic difference between the two, as long as they are not massively curved. But by definition, always keep in mind that we talk about the projected area only. So this is the one which we have meant. And I have just encircled the figure that I had drawn while teaching this concept. So if you go back to that part of the lecture, you can correlate well with this idea. And that's exactly what you would be plugging in here when it comes to the area expression, when you are working out the non-dimensional coefficients. For example, here it is the lift coefficient. This was the next question. Let's move on to the question raised by Anthony in lecture 5. In equation 4, shouldn't the second term in right-hand side have positive sign? So we'll try to work this out, for which we need to have a slightly detailed recap of what the question is about. We need to talk about, first of all, nomenclatures that we have used over here. So we were talking about calculation of normal and axial force per unit span acting on the airfoil. So when we say unit span, it is normal to the plane in which we draw the airfoil section. So it's along the Z direction. So here we assume that that length happens to be unity in consistent units. And the sign convention is very, very important here. The sign convention for theta is that it's positive when measured clockwise from the vertical line to the direction of action of pressure, and the horizontal line to the direction of tau. So that's the positive theta that we are talking about. So following that convention, if you take 2 points, namely the A and A dash, these are the 2 points we are referring to. And you can figure out that these are points typically on the upper surface of the airfoil, looking at the shape or slopes. You can easily figure out that the theta here is positive, while the theta here is negative, and thereby it will have profound implication on the signs of sine and cosine terms, which will figure in the expressions for the dnu, the dau equations that you write for the upper surface. Since it's the upper surface, of course, we use the subscript u wherever it is applicable. And N is for the normal force, A is for the axial force. And I hope all of you also recall how we make use of the angle of attack in order to convert the normal axial forces to the lift and drag forces. Here, of course, we are concerned more about the normal and axial forces only. So following the sign conventions and following the appropriate direction in which a normal force or axial force component due to pressure or shear stress will act, these equations are going to work consistently. When it comes to the sign convention, etc., we can do a detailed analysis to figure out whether they are consistent. So if we refer to figure 1, it's the point A dash. The figure 2, it's the point A once again. And in figure 1 at point A dash, we expect the NUP would be negative. That is pointing along the negative y direction because P is pointing downwards. Since tau is pointing upwards, Nu tau is expected to be positive. According to sign convention, since theta at A dash is negative, minus Pu dSu cos theta will have a negative value as cos theta is greater than 0, and minus tau u dSu sin theta will have a positive value as sin theta is less than 0. Thus, the equation 1 that we have for the differential normal component of velocity acting from the pressure and tau which are applied at the point A dash rather, with a small width ds, have consistent signs. So they give consistent signs for NUP and NU tau at A dash respectively. Following similar logic, AUP would be positive, that is pointing along positive x direction because P is tilted towards the right, and AU tau would also be positive because tau is tilted towards the right. The consistent positive signs are maintained by the terms minus Pu dSu sin theta, which happens to be positive because sin theta is less than 0, and tau u dSu cos theta, positive as cos theta is greater than 0. Similarly, in figure 2 at point A, we expect NUP would be negative since it's pointing along minus y direction broadly because P is pointing downwards. That's always the case for the upper surface of the airfoil. It's exactly opposite on the lower surface of the airfoil. Since tau is also pointing downwards, Nu tau is expected to be negative as well. According to the sign convention, since theta at A is positive, minus Pu dSu cos theta will have to be a negative value as cos theta is greater than 0, and minus tau u dSu sin theta will be negative as sin theta is greater than 0. Thus, the equation 2 gives consistent signs for NUP and NU tau at A respectively. Following similar logic, AUP would be negative, pointing along minus x direction because P is tilted towards the left, and AU tau would be positive because tau is tilted towards the right. The consistent signs are maintained by the terms minus Pu dSu sin theta, negative value because sin theta is greater than 0, tau u dSu cos theta, positive value because cos theta is greater than 0. So we could in detail see how it works for two such points A and A dash on the upper surface of the airfoil. If you go about doing it for two different points on the lower surface, namely B and B dash, then you end up having a similar outcome over here. Let's try to go through that. And if you go through that, finally you will notice that there is a typo over here. There has to be a correction plus, as you have correctly pointed out, and therefore if we make that correction, then the proper signs will be accounted for. So in figure 3, at point B, we expect NLP would be positive, that is pointing along positive y direction because P is pointing upwards. That's what we were saying earlier, that on the lower surface of the airfoil, the pressure will always have an upward sense, while on the upper surface of the airfoil, it's always in the downward sense. Since tau is pointing downwards here, NL tau is expected to be negative according to sign convention. Since theta at B is a positive value, remember that we have to go clockwise from vertical to reach pressure, and we have to move down from the horizontal to reach tau. Therefore, the theta is positive at B, so PL DSL cos theta will have a positive value as cos theta is greater than 0, minus tau L DSL sin theta will have a negative value as sin theta is greater than 0. Thus, the equation 3 gives consistent signs for NLP and NL tau at B respectively. Following similar logic, ALP would be positive, that is pointing along positive x direction because P is tilted towards the right, and AL tau would be positive because tau is tilted towards the right. The consistent signs are maintained by the terms PL DSL sin theta, positive value because sin theta is greater than 0, and plus tau L DSL cos theta, positive value theta is 0. And that's exactly where we need to have a correction. And you are correct in pointing this out. In figure 4, at point B dash, we expect the NLP would be positive, pointing along the upward direction. Since tau is pointing upwards, NL tau is expected to be positive. According to sign convention, at B dash, theta is negative. PLDSL cos theta will have a positive value as cos theta is greater than 0, minus tau L DSL sin theta will have a negative value as sin theta is less than 0. Thus, the equation 3 gives consistent signs for NLP and NL tau at B dash respectively. Following similar logic, ALP would be negative, that is pointing along the negative x direction because P is tilted towards the left, and AL tau would be positive because tau is tilted towards the right. The consistent signs are maintained by PL DSL sin theta, which is negative because sin theta is less than 0, and tau L DSL cos theta because positive value of cos theta is involved in that expression. So thank you for being very attentive and pointing this out. We did a detailed consistency check here, which would be beneficial for all the students. We move on to the next question. It's from assignment 1, question 11. So many of you have crossed this assignment several days back, and it may be again useful to have a look at these kind of problems, because those of you who may be interested in writing the final exam may need to revise all this. And even if you are not, then learning all that you are solving, all that you are going through very thoroughly is always helpful. So here the problem was that we had a wedge with 5-degree half wedge angle at 0 angle of attack, and free stream pressure and density are stated, and they correspond to the standard sea level conditions. Pressure on upper and lower surfaces of the wedge are constant with distance s. S essentially is the running coordinate moving along the surface, and the pressure is equal to each other on the upper and lower surfaces because of the symmetry of the geometry as well as of the flow at zero angle of attack. The chord length of the wedge is given, and the total drag force has to be worked out. So students have faced a little bit of difficulty working this out, it seems. And one of the students said that the span of the wedge is not given. So if it is not given, then we, of course, assume unit span. And let's see how we can proceed with the solution. So we'll associate subscripts U and L for upper and lower surfaces of the wedge. And you might have seen in the previous figure that there are important points that have been indicated here. S1 is essentially the leading edge. S2 is the right top corner. S3 is the point exactly at the center of the base of the wedge. And S4 is the bottom right corner. So having said that, we need to keep track of these points. And then when we go to finding the drag force, we understand that since it's at a zero angle of attack, it's the same as the axial force. And note that we have put a dash on both because the calculations are done for unit span. Thus, the drag can be obtained using an expression like this, where we go from leading to the trailing edge. Remember, here the trailing edge happens to be the midpoint of the base region of the wedge. That's what is considered as the trailing edge. Now, again, we have to be careful about sign convention for theta. And when we are integrating over the upper surface, for example, we go from S1 to S2 on the inclined surface, followed by S2 to S3 on the base. And while we go along the bottom, we go from S1 to S4 along the inclined surface and S4 to S3 on the base. So thereby, you have to be a little careful when you work out these integrals so that the limits are put properly and the orientation of the surfaces in terms of angles are accounted properly. So when it's the upper surface, the limits along the inclined surface, they mean to be like S1 to S2, and you use the appropriate inclination of the surface. Notice that this is going counterclockwise, and when it will be the lower surface, on the other hand, it will be clockwise, and therefore there's a difference in sign. Additionally, when you move along the base part from the top right corner to the middle of the base, the angle should be noted carefully, and there's an exactly opposite sign that is used when you move from the bottom right to the mid of the base. So these are the differences which you have to be a little careful about. If you are not using the proper sign convention, then very wrong numbers will be yielded out of the calculations. Note that when it comes to drag, whether it's pressure or it's shear stress, it's always going to yield positive values as long as you are talking about a viscous situation. So here, though we haven't solved viscous equations to generate these numbers, but they have been given in such a manner that they do simulate a situation somewhat similar to that. You find that equal contributions come from the upper and lower sections of the body, and they yield the same contribution to the drag. And the symmetry of the geometry and the flow essentially leads to this. Taking account of the shear stress distribution again, you have been given the functional form of variation of the shear stress. So that's what you plug in over here, and then you integrate, and then you put the suitable integrals, the limits in the integral, again noting that S1 to S2 on one side, S1 to S4 on the other, and so on. And you will find that in the base region of the body, you didn't have any difference with respect to the free stream pressure, and nothing was stated about the shear stress. Therefore, these facts also have to be appropriately fitted into your calculations when you do them. And you find finally that this is all that you need to account for in terms of the skin friction contribution. And you earlier worked out the pressure drag in the previous slide. Now you have worked out the skin friction drag, and you sum them, and you will find that the total drag value per unit span of the body comes to a form like this. So this is basically how we work out the problem. And if you couldn't manage to solve it, it's a good time to relook at it once more so that it will be useful for your future studies and also for exam if you are appearing for it. We have another query from Anthony, where he has posed a question regarding lecture 6. Here for CA, shouldn't it be CP lower times slope lower minus CP upper into slope upper? And for the pitching moment about leading edge, shouldn't the second term in bracket be added instead of subtracted? Well, it's an interesting question, but scrutiny reveals that this seems to be fine. What you need to do when you find time is try to integrate the normal and axial force differential relations over the entire airfoil. Similarly, integrate the momentum equation, which you can frame by taking moments of the forces about the leading edge. And finally, substitute these relations, which we have boxed over here, the non-dimensional force coefficients for lift, drag, and pitching moment. Note that for pitching moment, you have a c square in the denominator, and all through we are assuming unit span to calculate the planform area. The S therefore turns out to be C alone. And this is the pressure coefficient. This is the skin friction coefficient. We have, for simplicity, we have represented the dynamic pressure as Q infinity. So that's nothing but half rho U square, taking the values from the free stream. Additionally, you have to substitute dx equal to ds cos theta, and dy is equal to minus ds sine theta, so that you have a correct conversion between the s and the xy variations as you move along the surface of the body. So you can also work out this geometrical issues. Additionally, there are a few more points you need to take care of when you derive and check the consistency. So the yu is directed above the x-axis, and hence it's positive, while yl is directed below the x-axis, and hence it's negative. Also, the slope dy dx on both upper and lower surfaces, they follow the usual rules of calculus. So they are positive for those portions of the body with a positive slope, negative for those portions of the body with a negative slope. So putting all this together into the expressions that we have derived should be able to fulfill the requirements and prove that these equations are kind of consistent. So you can do that as a homework later. We have another query from Anthony over here. For the right-hand side of the bottom equation, shouldn't the first term be this? So usually we do not very explicitly mention on this, but if you look at The non-dimensionalization, I think you will find that it's we do not always associate this half factor that you have talked about, but yes, we do associate the the Q in infinity or Q, whatever you call it. So we are going to discuss about that a little bit over here, as you have rightly pointed out that there should be explicit mention of this factor, but how you would like to explain it is like this, that the second equation is the non-dimensional incompressible Navier-Stokes equation. It's the X momentum equation. In the dimensional form, when we divide all terms by the density, the pressure gradient term on the right-hand side will look like this, as we all know. In that case, the terms on left-hand side of the equation would not contain the density term anymore. When you have the above non-dimensional form, the pressure term is most often interpreted as the dimensional pressure by rho u infinity square. So we keep it at that, and therefore this is essentially what represents the P over here. So this P obviously is the dimensional P divided by rho u infinity square. If you wish, you can associate a rho infinity u infinity square. So that's the clarification for that question. Tushar has a question here regarding velocity gradients and viscosity. Over here, the shear is supposed to be vanishing as it reaches the boundary layer, but in accordance to the velocity profile, the velocity at the topmost point is maximum. It becomes free stream velocity. If we put that in the equation for, I guess, tau, we can get a significant value for shear stress at the boundary layer. I guess you mean boundary layer edge, the edge of the boundary layer, where we essentially reach the free stream conditions. Now, the point that we are trying to make is that, let's say if we make a velocity profile like this to indicate the boundary layer. So this is basically the delta, the thickness of the boundary layer. This is the wall along which the flow is moving. And this is essentially the velocity profile within the boundary layer. As you can understand that as we gradually reach the y equal to delta, the velocity change with increase in y becomes insignificantly small. So that's a very important fact that we have to keep in mind. While the rate at which the velocity changes as y changes is extremely large when we are near to the wall. So these two facts are extremely important and need to be appreciated when we talk about boundary layer. When it comes to the shear stress, for a flow like this, we can show very easily that it's primarily dominated by del u del y. Del v del x is way smaller than del u del I, and for all practical purposes, for a flat plate kind of flow, we might neglect it. Now, what happens to del u del y as we approach y close to delta? We'll find that the velocity gradient tends to 0. And therefore, the tau xy will also tend to 0. So though the velocity is becoming large, it's tending towards u infinity as you go to the edge of the boundary layer. The velocity gradient and not the velocity is what is going to matter as far as the shear stress is concerned. And therefore, you need to look at this difference when you try to distinguish. So, as I said, that the velocity maximizes, but at the same time, the velocity gradient becomes minimum. And therefore, the shear stress also becomes minimum in the sense that it tends to 0. We are not, of course, talking about a situation where the boundary layer kind of flow breaks down and there's a flow separation. In such cases, these rules may be broken, velocity gradients can become negative, shear stresses can also change sign, but that is a different matter altogether. That's related to flow separation. As long as it is a boundary layer kind of flow, this is the model which you need to understand and appreciate. So I hope that question is resolved. Another question from Anthony regarding shock waves, oblique shock waves. So he has talked about this image where we tried sketching the theta beta m relation for different Mach numbers, and we explained that the envelope becomes wider and wider as the Mach number increases. So this is the direction of Mach number increase. The different envelopes indicate that they are going to higher Mach numbers gradually. And for a given Mach number, if we talk about a theta which is going beyond these dashed lines, then we won't have an attached oblique shock. We'll have a situation like this, a detached curve shock. While as long as we keep within the envelope, we get attached oblique shock. So in the second image for the lower side of the flat plate, since theta is which is equal to alpha, that is the angle of attack, is less than theta max, shouldn't two shocks be formed? That's the question. So the basic idea is that the flow gets compressed as it moves along the lower side, creating a straight oblique shock that we have indicated over here. Note that the theta beta m plot indicates that for the same upstream Mach number, there can be two straight oblique shock solutions. Normally, it is the weak shock solution which gives the lower value of the wave angle beta. This is an important point. At no point can both the cases coexist. So this is not possible. Since there are two distinct cases occurring on the two branches of the curve, hence only one shock can form. So that's basically the answer to your question. And for all practical purposes, you may assume this to be the weak shock solution. The shock gets detached from the body if theta is greater than or equal to theta max for the given upstream Mach number. In the theta beta m diagram, sketch the theta greater than theta max would lie beyond the curves along the x-axis. In the above problem, that is not the case, and therefore you have a straight attached oblique shock. You may recall that as the flow moves down, near the trailing edge of the flat plate, there will be an oblique shock formed on the upper surface, and an expansion fan moves downstream of fan formed on the lower surface as the flow moves downstream of the body and adjusts to the local free stream conditions. So that's again something that you need to recap, that we are talking about a shock here, we are talking about expansion here, and how that helps the flow to cope with the local free stream conditions. You may also recall that there's another feature, it's a slipstream, which will occur, which will kind of act as a demarcating boundary between the upper and lower flows. There are a few other queries which are not strictly technical, not all of them technical. So there was a question 4 and options regarding question 4 which had some ambiguity. However, the TAs of our course have meticulously checked, and we could not find any anomaly in the options in any one of the assignment 4th questions till date. So if you still have any issues, please write in the forum. We'll try to take care of that. That's from Anirudh. Kanak had a problem in accessing the Google Drive link to the week 2 lecture material. I hope that has been addressed by now. There's a question from Vijay Prakash regarding credit points of the course, for which I would suggest that you look at the Swayam website, which is pretty much very well informative, and I think that should be enough for you to address this question. There was a query from Manthan Warren regarding problem-solving sessions. So, though we do not have any provision for any specific problem-solving sessions, and neither are they planned, I'll be taking at least 2 live sessions, one of which was held today. And if you have specific problems, please write in the forum, and we'll take them up in the live sessions. Additionally, our TAs keep tracking your emails and responding from time to time. So put together, I hope you will have a very fulfilling experience, and we should be able to address your concerns and doubts as far as possible. And I keep encouraging you to write to us, keep participating very actively with us in learning the course. Please reach out through the forum, and we'll try to keep interacting with you. And I hope that you will have a very enjoyable learning during the remaining weeks of the course. For those students who are going to appear for the final exam, keep learning each week's content diligently and practicing your assignments. I'm sure you'll be able to do very well in the final exam too, if you do that. With that, I come to the end of this first live session of the course. Thank you very much for your active participation. And on behalf of the entire team comprising of the TAs, myself, and the entire technical team, which is supporting us in all possible ways, I wish you all the very best. Thank you.